Come on, my dears, let us proceed further in chapter number 8. Today we will begin with article propagation of energy through wave. How does wave carry energy with it? I am showing you. Look, consider this example. Take this as calm surface of water. Okay. Here we have some matchbox which is steady and floating on the surface of water. Okay. So this is a matchbox. Okay, fine. Now what we do, we just keep some spherical bob on the surface of water and we start giving it up and down oscillations. Correct? Fine. Now to give it up and down oscillations, we are doing mechanical work on it, we are spending mechanical energy. Now that energy spent by us is assumed by this bob and hence the subsequent particles in the form of energy of oscillation, that is mechanical energy. You know, mechanical energy is summation of kinetic and potential energies. So during the oscillation, that energy is partly kinetic, partly potential. Okay, fine. Now, as you are giving the energy continuously through this spherical bob, that energy is possessed by the subsequent particles coming in the direction of propagation of wave, turn by turn. Okay, fine. One by one, they all receive that energy. Now, how we are sure that all the particles coming in the way, turn by turn, receive the energy? How we are sure? I am showing you. After some time, you will notice that this matchbox also starts performing oscillations, correct? This way, up and down. Now tell me, if matchbox is oscillating up and down, it means that it also must have energy of oscillation. But now question arises, we have not given directly that energy to that matchbox. No, we have not given that energy to the matchbox directly. Actually, we are supplying energy to this very particle. Okay, but then from here to here, it is the wave which carries the energy, and that's why after some time, when that energy is delivered at this particle, then after when that particle is oscillating, naturally the matchbox which is lying above that particle also has to oscillate up and down. Correct? So I mean to say, the energy which you are providing in the medium here, that energy propagates in the medium, it comes from here to here and further so on. Okay, fine. So as the wave propagates, what does wave do? It carries energy with it. It transfers energy from one place to another place. Waves carry energy with them. Waves carry energy with them. Correct? Through the propagation of wave, we have propagation of energy. Fine. Now onwards, if anybody tells you that in a typical medium, there are waves propagating in typical direction, you must understand in that direction actually energy is propagating. Okay, fine. Now what happens as this wave propagates ahead and ahead, we find that it is getting damped. Its amplitude goes on decreasing. Why amplitude goes on decreasing? Quite natural, because when this energy is propagating, come on, that all the particles, they are oscillating, correct? But this medium in which the particles are oscillating offers some internal resistance to the oscillations of those particles. So in order to overcome that internal resistance, the oscillating particles have to spend their mechanical energy. So naturally, when mechanical energy is spent, gradually it will decrease, and you know mechanical energy is directly proportional to square of amplitude. So when mechanical energy decreases, then naturally amplitude will also decrease, and that's why here you can see, compared to this amplitude is smaller, compared to this amplitude is smaller. As the wave propagates ahead and ahead, amplitude goes on decreasing. When amplitude is going on decreasing, we say the proceeding wave gets damped because its amplitude goes on decreasing. You know, oscillations in which amplitude goes on decreasing are called damped oscillations, correct? Fine. What about intensity of wave? Shown by symbol I. Don't draw this figure in the examination, but just for your kind knowledge and understanding, I have drawn that figure here. Consider this as bulb of light. When you just make it switch on, it will start emitting light energy, correct? And that energy propagates in the form of light waves. You just consider one typical direction of propagation of wave. Say this direction. Fine. Now you just do one thing. Consider one plane area which is perpendicular to this direction, correct? And that area has the value 1 unit. And through this area you can see light energy is passing through this area. But the time for passage of energy, you just allow unit time, 1 unit time. Then whatever amount of energy passes through this area in unit time, which is chosen perpendicular to direction of propagation of wave, that very amount of energy itself is known as intensity of wave. Amount of energy passing through unit area chosen perpendicular to direction of propagation of wave in unit time is called intensity of wave, shown by symbol capital I. Amount of energy passing through unit area chosen perpendicular to direction of propagation of wave in unit time is called intensity of wave. Last time, amount of energy passing through unit area chosen perpendicular to direction of propagation of wave in unit time is called intensity of wave, shown by symbol I, correct? Fine. Tell me, if you really understood the definition of intensity, you can definitely dictate me the unit of intensity. Very simple. After all, tell me, what is intensity? It is some sort of energy. Then what is the unit of energy? Joule. Is it simply energy? No, it is energy per unit area. So you must divide by unit of area, which is meter square. It is simply energy per unit area? No, it is energy per unit area per unit time also. So now you must divide by unit of time, which is second, correct? Now tell me, joule upon second, it is nothing but what? You know, work upon time. Work upon time will give you power, and SI unit of power is watt. So in place of joule upon second, you can write watt, that is capital W upon small m square as it is. So what is the SI unit of intensity of wave? Watt upon meter square. Watt upon meter square. Got it? Fine. What about dimensional formula of intensity of wave? Come on. Energy upon area into time. What about for energy? M raised to 1, L raised to 2, T raised to minus 2. Divided by, for area, L raised to 2. For time, T raised to 1. Correct? Now M raised to 1 as it is. L raised to 2, L raised to 2 will get cancelled. Then L raised to 0. T raised to minus 2 minus 1, that is T raised to minus 3. M raised to 1, L raised to 0, T raised to minus 3. In the first semester, you have studied this dimensional formula. You must remember now. For intensity, it is M raised to 1, L raised to 0, T raised to minus 3. Got it? Fine. Then remember, intensity of any type of wave is definitely directly proportional to square of its amplitude. Intensity of any wave is always directly proportional to square of its amplitude. So mathematically you can write I proportional to A square, and then after for the numericals you may remember 1 2 1 2, that is I1 upon I2 equals to A1 square upon A2 square. I1 upon I2 equals to A1 square upon A2 square. Simple? Fine. What do you mean by wave number? Wave number. Tell me. Lambda is the length of one wave. So this is one wave, its length is this much, which is lambda. So you can see from the diagram, if I take the distance equal to lambda, then the distance equal to lambda, how many waves are accommodated? Only one wave. Only one wave is accommodated. So in distance lambda, number of waves accommodated is only one. Then question arises, how many waves can be accommodated in unit distance? So per unit distance, how many number of waves can be accommodated? This into this upon this. In distance lambda, if one number of wave can be accommodated, then in unit distance, how many number of waves can be accommodated? This into this upon this, that is this into this means 1 upon lambda, correct? So 1 upon lambda will give you number of waves in unit length, and that number of waves itself is known as wave number, wave number. So this 1 upon lambda which gives you number of waves in unit length along the direction of propagation of wave, and that very number is called wave number, correct? What about SI unit of wave number? Very simple, 1 upon meter, 1 upon meter, that is meter inverse, okay? What about wave train? Wave train, I am showing you. Consider a thin string which is stretched and kept under proper tension. When you produce disturbance of simple harmonic type in the very first particle, at that time, at the end of one oscillation, that is at the end of capital T time, don't you know this sort of shape is produced in the string, correct? This is called trough, this is called crest, fine. Now if you give second oscillation to this particle, correct, then what will happen? Then you will have one more shape like this, correct? At the end of one oscillation you are going to have this shape, then at the end of second oscillation you will have one identical shape, produce another one. That second shape is now taking place of first shape. First shape will move ahead, it will come here. Now give third oscillation to this particle, correct? Third oscillation, then time taken will be 3 into capital T, 3 into capital T. At the end of time 3 into capital T, what will be the pattern in the medium? I am showing you. When you give third oscillation here, such identical third shape will be produced. It will come here in place of second shape. Second shape will proceed ahead, will move ahead. It will come in the place of first shape, and first shape will move ahead. It will come here, correct? So tell me, if you are producing disturbance here continuously, suppose continuously, then continuously you will have production of the shapes one after another, and all those shapes will just travel ahead and ahead together simultaneously. Such a non-stop motion of disturbance propagating in the medium is called wave train. Non-stop motion of disturbance is called wave train. Motion of disturbance is called wave, but non-stop motion of disturbance is called wave train, correct? When you are talking about a single wave is getting damped as it travels ahead and ahead, correct? So after some distance it may stop also. So a single wave stops after covering some distance, but when you are talking about wave train, it is non-stop motion of disturbance, okay, which is called wave train. Non-stop motion of disturbance is called wave train. Fine. Now let's go for classification of waves. Different types of waves you can classify according to two bases. First base is regarding requirement of medium. If medium is required, then such waves are called mechanical waves, and if medium is not required, such waves are called non-mechanical waves. Fine. And then second basis is on the basis of direction of oscillation of particle of medium. If direction of oscillation of particle of medium is perpendicular to direction of propagation of wave, then such waves are called transverse waves. And if direction of oscillation of particle of medium is parallel to direction of propagation of wave, then such waves are called longitudinal waves. Let us see one by one. First of all, mechanical waves. All those waves which are propagating in the elastic media, during the propagation of which particles of the medium take part in the process of propagation, are called mechanical waves. For example, sound waves. When the sound waves propagate through the air medium, the air particles take part in the propagation of wave, correct? So they are mechanical waves. You can say string waves, because during the propagation the particles of string take part in the process of propagation. Then water waves. At that time also the particles of water medium take part in the process of propagation, correct? Sound waves, string waves, water waves, they are all mechanical waves. What about non-mechanical waves? A wave for the propagation of which no medium is required is called non-mechanical wave. For example, electromagnetic wave, in which light wave is already accommodated. Electromagnetic wave are those waves which can propagate even in vacuum. In the absence of all types of media, in vacuum also they can propagate, meaning thereby for their propagation no medium is required. That's why they are called non-mechanical waves, correct? Waves for the propagation of which no medium is required are called non-mechanical waves. Simple. What about transverse waves? See, during the propagation of wave through the string which is stretched and kept under proper tension, you can see the direction of propagation of wave is this, but during that propagation what happens? The particles of string, they oscillate up and down, that is perpendicular to direction of propagation of wave. If direction of oscillation of particle of medium is perpendicular to direction of propagation of wave, then such wave is called transverse wave. The waves propagating on the water surface, they are transverse waves. Waves propagating in such a string, they are transverse waves. And you will study in third semester, the electromagnetic waves are also transverse waves. How would you define it? During the propagation of given wave, if particles of medium oscillate in a direction perpendicular to direction of propagation of wave, then that wave is called transverse wave. Okay? What about longitudinal wave? Longitudinal wave. During the propagation of sound waves in air, it so happens that along the passage of sound waves, the phenomena called condensation and rarefaction take place. And during the phenomena of condensation and rarefaction, you know, particles of air medium, they oscillate to and fro like this. That is parallel to direction of propagation of sound wave. Such waves are called longitudinal waves. Waves during the propagation of which particles of medium oscillate parallel to direction of propagation of wave are called longitudinal waves, and we have only one example for longitudinal waves, they are sound waves. Okay? I repeat, waves during the propagation of which particles of medium oscillate parallel to direction of propagation of wave are called longitudinal waves. For example, sound waves. Okay? Then we go for what are called progressive waves. Waves which travel ahead and ahead continuously away from the source are called progressive waves. Waves traveling ahead and ahead continuously away from the source are called progressive waves. Then we go for harmonic waves. During the propagation of wave in a medium, if particles of that medium oscillate in a direction, I'm mistaken, if particles of that medium are performing simple harmonic motion about the respective equilibrium positions, then those waves are called harmonic waves. I repeat, waves during the propagation of which the particles of medium perform simple harmonic motion about their respective equilibrium positions are called harmonic waves. In textbook they have written that if harmonic wave is propagating in one dimensional medium, then it produces curve like sine curve or cosine curve. Yes, it is true, provided progressing harmonic wave is transverse wave. If progressing harmonic wave is transverse wave, then only the curve produced in the medium, the pattern developed in the medium is like a sine curve or cosine curve. But if that progressing harmonic wave is longitudinal wave, then sine or cosine curve is not getting produced. Okay? So you must add in the definition, you must write in bracket that way, that if progressing harmonic wave is transverse, then only in one dimensional medium we get shape produced like a sine curve or cosine curve. The way we are getting here. This is nothing but sine or cosine curve. Correct? I repeat, during the propagation of progressing harmonic wave, if it is transverse wave, then the pattern developed in one dimensional medium is like a sine or cosine curve. Correct? Fine. Then we go for matter waves. Matter waves. In third semester you will study that tiny materialistic particles, whenever they are in a state of motion, they behave as if they are waves. and then such waves are called matter waves, and the wavelength of a wave which represent their motion is called matter wavelength, and it is shown by symbol lambda. Its formula you have derived in first semester using dimensional analysis. That formula you will derive once again in third semester using another approach. That formula, right now you don't need to remember this formula, just for your kind knowledge. Lambda equals to h upon mv, where h is Planck's constant, m is mass of a given tiny materialistic particle, v is the velocity during its motion. Correct? Fine. Wave having this much wavelength is called matter wave, and the corresponding wavelength is called matter wavelength. Okay? Fine. What about pressure waves? Pressure waves. Consider this tuning fork, correct? These are the pronges of the tuning fork, and when you strike this tuning fork with a rubber pad, naturally these pronges will start vibrating, correct? During their vibrational motion, it so happens that in the neighboring region, the pressure and density go on changing periodically. At a given moment, if in the neighboring region pressure and density have been increased, then in that region the particles will come very close. In that region we say condensation has taken place. At the same moment in the neighboring region, you will find that region in which pressure and density have been reduced. In that region we say rarefaction has taken place. So condensation and rarefaction are taking place alternatively. Okay, this is the situation at a particular moment, but at later moment, say after half of the periodic time, the condensation and rarefaction, they interchange their positions. In place of condensation you will find rarefaction, in place of rarefaction you will find condensation. Okay, but tell me, actually what is happening here? During the motion of this right hand side pronge, on the right hand side this way, the pressure is increased here, and that's why density is also increased. But then after, the region of higher pressure and higher density goes on traveling this way, away from the source, correct? So because the region of higher pressure and higher density goes on traveling, we call such waves as pressure waves, okay? Region of higher pressure and higher density is traveling ahead and ahead away from the source, okay? Fine. Distance between two consecutive condensations is called wavelength, lambda, or you may say distance between two consecutive rarefactions is also lambda. Here, if you are talking about given position, then pressure and density go on changing periodically with time. If you are talking about given moment of time, then pressure and density go on changing periodically with the distance. Okay. So pressure and density go on changing periodically with distance also at a given moment, and go on changing periodically with time at a given position. Got it? Fine. What about seismic waves? Look, during the earthquake, whichever waves propagate on the surface of earth are called seismic waves, and those seismic waves are found to be of two different types. One is called S wave or secondary wave, another is called P wave or primary wave. This secondary wave is found to be transverse in nature, whereas this primary wave is found to be longitudinal in nature. The speed of S wave is less, it is 2 to 5 km per second, Speed of primary wave is greater, it is 4 to 8 km per second. Okay. Now wait, suppose here is the epicenter from which the earthquake waves originate, okay, that is epicenter. But then naturally, after beginning, if the speed of P wave is greater, naturally it will travel longer distance in a given time. So if at some distance, if you have just kept some instrument which can note down the presence of earthquake waves, which we call seismograph, then at the seismograph, which will be the wave which is getting recorded first, naturally that wave whose speed is greater. Whose speed is greater? The speed of P wave is greater, okay, primary wave. So it is getting noted at the seismograph first, and after some time the another wave, that is S wave, is getting recorded. So we just note down the time difference between the recording of P and S wave, and after noting down the time difference, then we know the speeds. So accordingly we can calculate exactly at which position the earthquake waves must have arisen. That point is called epicenter. Okay, so we can locate the epicenter position from the position of seismograph according to this method. Okay, that instrument is called seismograph. Okay, fine. Wave equation for one-dimensional progressive harmonic wave. What do you mean by one-dimensional wave? A wave propagating in one-dimensional medium is called one-dimensional wave. A wave propagating in one-dimensional medium is called one-dimensional wave. You know what is called progressive wave? A wave which moves ahead and ahead away from the source continuously is called progressive wave. What about harmonic wave? During the propagation of wave in a medium, if particles of that medium start performing simple harmonic motion about the respective equilibrium positions, then that wave is called harmonic wave. Okay, fine. Now what do you mean by wave equation? Very simple. An equation with the help of which we can find out displacements of different particles taking part in the process of propagation of wave at different times is called wave equation. An equation with the help of which we can find out displacements of different particles at different times taking part in the process of propagation of wave is called wave equation. Okay, fine. In our syllabus, first we have to derive the wave equation for a wave which is one-dimensional, harmonic and propagating along positive x-axis. So take this as positive x-axis and take this also as a thin string which is stretched and kept under proper tension. Now what we do in this very first particle, we start producing disturbance of simple harmonic type at time t equal to 0, fine. And when you finish one oscillation, correct, at the end of one oscillation the time lapse must be equal to periodic time, correct. At the end of capital T time, the disturbance which was produced here, this travels this much distance and it comes over here, correct. So you know in time t, the distance travelled by the wave is equal to wavelength of the wave shown by symbol lambda. So at the end of t time, the disturbance has come over here at say particle I, fine. Now tell me, in this t time, this very particle has finished one oscillation. So at the end of one oscillation, its phase becomes 2 pi radian because its initial phase was 0. Now come on, at the end of capital T time, phase for this particle has become 2 pi radian. At the end of same capital T time, the disturbance has just arrived here, yet this particle has not started oscillating, then its phase would be 0 at time capital T. So at time capital T, phase of this particle is 2 pi, phase of this particle is 0. Then what is the phase difference between these two particles? It is 2 pi minus 0, that is 2 pi radian. And you know the distance between two particles having phase difference of 2 pi radian at any one instant of time along the direction of propagation of wave is called wavelength of the wave shown by symbol lambda. So length of one wave is called wavelength, that is lambda. Simple, fine. Now you are talking about harmonic wave. You are talking about harmonic wave. And whenever harmonic wave propagates, each and every particle performs simple harmonic motion about its equilibrium position. First of all, you talk about this first particle from which the wave starts propagating, which we call origin of wave. Origin of wave. What would be the displacement of this particle? Because each and every particle performs simple harmonic motion, then you can treat every particle as simple harmonic oscillator. And for a simple harmonic oscillator, don't you know equation of displacement? What is it? Y equals to A sin omega t plus 5. Y equals to A sin omega t plus 5. But phi is 0. Phi is 0. Correct? So I am writing here omega t. Because we had oscillated this particle first towards the positive end of the path after beginning from fixed point. Correct? That's why its initial phase is 0. Now tell me, this bracketed part along with this sine function gives you phase. So this will give you phase of particle A at the end of t time. Correct? Now consider another particle, say particle G. Consider this very particle which is at distance x from this source. Okay. Now tell me, as the time passes on, what will happen? The energy is given to the subsequent particles. So all these particles will start oscillating. What I mean to say, very first particle starts oscillating very first, then after this particle, then after this particle, then after this particle, like that. So what I mean to say, as you proceed away from the source, the particles coming in the wave will have smaller and smaller phase, For example, at the end of capital T time, what was the phase for this particle? It was 2 pi radian. And at the same time, what was the phase for this particle? It was 0. So when you move away from the source, phase decreases. When you move away from the source, phase decreases. So one thing is sure, phase of this particle must be less than phase of this particle, correct? Because it is at distance x away from the source. So phase of particle G should be less than this phase, less than omega t. So I am writing here omega t minus delta. Less than omega t means I am writing omega t minus delta. So what is delta? Phase difference between particles A and G, or you can say it is decrease in phase at distance x from the source. So delta is nothing but decrease in phase at distance x from the source. I repeat. What is the phase of particle A? Phase of particle A, it is omega t, correct? But when you move away from the source, what happens? Phase decreases. So at the same time t, small t, I should get phase of particle G smaller than this phase, smaller than omega t. So I am writing omega t minus delta, correct? Where delta is nothing but decrease in phase at distance x from the source. Delta is what? Decrease in phase at distance x from the source. How would you find out the value of delta? Very simple. Just move away from the source, say by amount lambda, by distance lambda, and then decrease in phase, you see 2 pi minus 0. 2 pi minus 0, that is 2 pi radian. So when you move lambda distance away from the source, distance from the source is lambda, then decrease in phase is by amount 2 pi radian. Then if I move x distance away from the source, what should be corresponding decrease in the phase? If I move x distance away from the source, what should be decrease in phase? This into this upon this. That is 2 pi x upon lambda. 2 pi x upon lambda. This will give you decrease in phase at distance x, but decrease in phase at distance x from the source, it is nothing but delta. So this 2 pi x upon lambda is nothing but value of delta. Got it? Delta equals to 2 pi x upon lambda. Delta equals to 2 pi x upon lambda. Just put it here. Value of delta, we have found out it. What is the value? Delta equals to 2 pi x upon lambda. Delta equals to 2 pi x upon lambda. Correct? But don't you know, 2 pi upon lambda is nothing but wave vector of a wave shown by symbol small k. So in place of 2 pi upon lambda, I can write small k. Correct? So y equals to a sine omega t minus 2 pi upon lambda is nothing but small k into x. Correct? Now tell me, if you change this x, then you are taking into consideration some different particle. Correct? So by changing x, we can change the particle. By changing t, we can change the time. So displacements of different particles can be found out using this equation at different times. That's why this equation is called, according to definition, wave equation. Just recall the definition. An equation with the help of which we can find out displacements of different particles at different times taking part in the process of propagation of wave is called wave equation. An equation with the help of which we can find out displacements of different particles at different times taking part in the process of propagation of wave is called wave equation. Correct? So this is nothing but wave equation for a wave which is one dimensional, progressive, harmonic and propagating along positive x-axis. Correct? But now let us obtain some other equivalent formats of the same equation. I am showing you how to get it. Very simple. Come on, y equals to a sine as it is. Y equals to a sine as it is. But don't you know formula of omega? Omega is 2 pi by capital T into small t as it is. Correct? Minus k. What is k? Wave vector. What is the formula? 2 pi upon lambda into x. Fine. Now this 2 pi I can take common. Correct? Take out common this way. Okay? In textbook they have not written this bracket. Is very wrong. You must write this curly bracket. Okay? Come on. Y is equal to a sine 2 pi taken common. Inside the bracket small t upon capital T minus x upon lambda. X upon lambda. Got it? Fine. Now tell me. 1 upon capital T is nothing but frequency. 1 upon periodic time is frequency, which is f into small t minus, come on, x as it is. Don't you know formula of wave velocity? V equals to f lambda. V equals to f lambda. Then what is lambda? It is v by f. Lambda is v upon f. Lambda is v upon f. Denominator will become numerator. And now this f and this f you can take common. So it is 2 pi into f into bracket small t minus x upon v. Small t minus x upon v. And now tell me, frequency into 2 pi radian. Frequency into 2 pi radian is nothing but angular frequency shown by symbol omega into t minus x upon v. Tell me, all these blocked equations, they are wave equations, but in terms of different physical quantities I am showing you. This is wave equation, no doubt, but in terms of angular frequency and wave vector. This is no doubt wave equation, but in terms of periodic time and wavelength. This is wave equation in terms of frequency and wave velocity. This is wave equation in terms of angular frequency and wave velocity. Okay? If you are asked to derive wave equation in terms of angular frequency and wave velocity, then you can reach up to this step. Otherwise, in the examination, if it is simply asked derive wave equation, then you are supposed to derive up to this step only, which is very easy. Y equals to a sine omega t minus kx. Correct? What was this omega t? It was phase of first particle at time t. What is this omega t minus delta? It is phase of particle g or phase of that particle which is located at distance x from the source at time t. And as you move away from the source, what happens? Phase decreases. That's why this phase is smaller than this phase by amount delta. Correct? What was the delta? Delta was phase difference between these two particles separated by distance x. And what is the formula for delta? Delta equals to 2 pi x upon lambda. Got it? At distance lambda, the phase difference is 2 pi radian. Then at distance x, what is the corresponding phase difference? This into this upon this. That is 2 pi x upon lambda. Got it? Please remember this formula separately. We will use it in the numericals. Okay? Fine. Now let us talk about for negative x-axis. If the same wave propagates along this axis, look here this way, that is towards negative x-axis, then the only change that you have to make is replacing x by minus x. Replacing x by minus x. Replace x by minus x. So write minus x in place of x. Come on, write it here. In place of x, when you write minus x, minus will become plus. So you will get the wave equation y equals to a sine omega t plus kx. Here it is. Y equals to a sine omega t plus kx. I just suggest you one idea to remember. If the wave is propagating along positive x-axis, then for positive there is a negative sign here. And if the wave is propagating say along negative x-axis, then for negative x-axis there is a positive sign here. For positive there is a negative, for negative there is a positive. Simple? Fine. What about wave velocity? Wave velocity formula last time we had obtained. There were two formula for wave velocity. V equals to f lambda and also V equals to omega upon k. V equals to f lambda and also V equals to omega upon k. Correct? Give me identification. Wave velocity, frequency of wave, wavelength of wave, angular frequency of wave, wave vector of a wave. Got it? Fine. Another small but important interesting article about phase speed. About phase speed. Along the direction of propagation of wave, the speed with which the particles assume given constant speed is called phase speed. I repeat, along the direction of propagation of wave, the speed with which particles assume given constant speed is called phase speed. Now you may ask how. I am showing you. Consider this as a string which is stretched and kept under proper tension. Give one full oscillation of simple harmonic motion type to this very first particle, and then you know at the end of capital T time the shape produced in the string is like this, correct? And by that time the disturbance has come over here. At the end of capital T time, the phase of this particle is 2 pi radian, phase of this particle is 0, correct? Fine. This much distance is lambda. Now you just give second oscillation to this particle, second oscillation. Then what is the time lapse? Another additionally capital T time. So T plus T that is 2T. At the end of 2 oscillations, the time lapse must be equal to 2 times periodic time, correct? But then here second shape will be produced. We'll push this first shape ahead. So this is the second shape and the first shape has moved ahead. It has come over here. Fine. At the end of 2 oscillations, here the phase has become 4 pi radian. Here phase is 2 pi radian. Why? Because when this particle got the disturbance, it was timed capital T, correct? And now the time is 2T. 2T minus T, that is capital T. In capital T time, this particle finishes one oscillation. So from 0, its phase has been increased. Now it has become 2 pi radian. At the end of 2T time, the disturbance has just come over here. This particle yet has not started oscillating. So this phase is yet 0. Now tell me, what is this 2 pi radian? It is the phase of this particle, correct? At the end of how much time? At the end of capital T time. What is this 2 pi radian? Here also 2 pi, here also 2 pi. But this 2 pi is the phase of this particle, correct? Which is at distance lambda from the source of production of wave, correct? Now tell me, this is also 2 pi radian, this is also 2 pi radian. So 2 pi radian means constant phase difference, constant phase, okay? This is also 2 pi, this is also 2 pi. So we are talking about constant phase value, how much? 2 pi radian. But earlier it was here for this particle, now it is here for this particle. So the particle is now getting changed from here to here. The position of particle has been changed from here to here, and by that time how much distance is traveled? Distance traveled is lambda. In how much time? In a time 2T minus T, that is T time. So if distance traveled is lambda and corresponding time is capital T, and if the corresponding phase speed is V dash, then you know phase speed is after all speed only, and speed is nothing but distance traveled in a specific direction per unit time. So it should be lambda upon capital T, correct? And come on, 1 upon capital T, 1 upon periodic time is nothing but frequency into lambda. And don't you know F into lambda? F into lambda is nothing but wave velocity. So this can be replaced by wave velocity. In short, whatever is the wave velocity, same is nothing but phase speed. I repeat, the speed with which the particles along the direction propagation of wave assume given constant speed is called phase speed, correct? The constant speed, suppose you are taking 2 pi radian, then earlier it was for this particle, now it is for this particle. Tell me how much distance is covered, what is the separation between these two particles? It is lambda, but in how much time that distance is covered? In a time 2T minus T, that is T time. Distance traveled divided by time taken will give you speed, correct? And that speed is called phase speed, shown by symbol V dash, but 1 upon periodic time is nothing but frequency into lambda, correct? And come on, F into lambda is nothing but wave velocity, so I am writing V. So what we have proved, that phase speed is nothing but wave velocity, correct? But same result we have to prove using the method given in the textbook. Now tell me, what is the phase here? 2 pi radian. What is the phase for this? 2 pi radian. So 2 pi equals to 2 pi. So I am talking about constant phase value. How much? 2 pi radian. You may take any other value. At present I am taking 2 pi radian. Okay. So constant phase value which I am taking right now, it is 2 pi radian. So I am talking about constant phase. So phase is omega t minus kx. Let it be shown by symbol theta, which remains constant. Which remains constant. Wait. What is this omega t minus kx? Tell me. What is this omega t minus kx? It is phase of particle at distance x from the source of wave along the direction of propagation of wave at the end of t time after the wave has started propagating. I repeat, this bracketed part will give you phase of particle at distance x from the source at time t, and that phase is omega t minus kx, and that phase we want constant. So that phase which I am showing by symbol theta, I want value of theta to remain constant. Say that constant value is 2 pi, then here it is 2 pi radian, here also it is 2 pi radian, so that theta which is 2 pi has remained constant. So theta is constant, and once theta is constant, then anything which is remain constant with time, its derivative with respect to time should be 0. Because theta is constant, d theta upon dt should be 0. So now it is d by dt of a theta. What is theta? Omega t minus kx, and that should be equal to 0. Now come on, omega is constant, d by dt of t is 1, minus k is constant, dx by dt, that equals to 0. Omega into 1, that is omega, minus k as it is. This is the speed of constant phase. Let it be shown by symbol v dash, which we call phase speed. Let it be v dash, and that equals to 0. Now transfer this. From minus it will become plus. Find out v dash. It is now omega upon k. But don't you know omega upon k? Omega upon k is nothing but wave velocity. So this can be replaced by wave velocity. So what ultimately we have proved? Phase speed is equal to wave velocity. Phase speed equals to wave velocity. Correct? I repeat the definition of phase speed last time. Along the direction of propagation of wave, the speed with which constant phase is possessed by the particles is called phase speed, and that phase speed value comes out to be equal to value of wave velocity. That is what we have proved. Okay, fine. Here we have proved according to textbook method. Here I have proved the same result using this figure. Correct? Now for the third figure, suppose constant phase you are taking, say 4 pi radians. Suppose 4 pi radian. Then here 4 pi radian is the phase at the end of how much time? At the end of 2t time. The same 4 pi radian phase you will find here, but at the end of 3t time. Correct? So in order to have constant phase equal to 4 pi radian, the time interval required is 3t minus 2t, that is t. 3t minus 2t, that is t. And this particle is here, this particle is here. What is the separation between them? From here to here, that separation is nothing but lambda, or you may say 3 lambda minus 2 lambda, that is lambda. So that separation or distance traveled meanwhile is lambda, and distance traveled divided by time taken will give you speed. We call it phase speed. 1 upon periodic time is nothing but frequency. F into lambda is nothing but wave velocity. It is v. Correct? So whatever is the phase speed, same is the wave velocity. Fine. Then we go for small topic, very small formula. Come on, let us derive it because it will be utilized in the numericals. Okay? What do you mean by velocity of oscillation of a particle? Listen. When the wave is propagating in a given medium, correct, with whatever speed the wave is propagating, that is to be determined by the medium. If you change the type of medium, then that wave speed will change. Okay? But during the propagation of wave, you know these particles will perform simple harmonic motion in this case, and then each particle can be taken as simple harmonic oscillator. Then when simple harmonic oscillator is oscillating like this at different positions at different times, it has different velocity. So here I am talking about velocity of oscillation of particle. Velocity of propagation of wave is different, and velocity of oscillation of particle is different. During the propagation of transverse wave, velocity of particle is perpendicular to velocity of propagation of wave. Correct? Come on. In this direction, if wave is propagating, then during the propagation of transverse harmonic wave, particle is oscillating up and down this way. Correct? Both the velocities are mutually perpendicular. I am talking about at present velocity of oscillation of particle. That's why I am showing by symbol Vp, P for particle. Got it? Velocity of particle can always be found out by taking time derivative of displacement of that particle. D by dt of y will give you velocity. But because this is displacement of particle, I should get velocity of particle. Come on, d by dt as it is. What about expression of y? Y equals to s sin omega t minus kx. Y equals to s sin omega t minus kx. Now a is constant taken out, derivative of sine is cos, and now go inside the bracket, omega is constant, d by dt of t is 1, and when you are taking derivative with respect to time, you are talking about given particle. For a given particle, its distance from the source is constant. In short, this part is constant, and derivative of constant part would be 0. Now come on, a into omega, I am writing into cos of omega t minus kx. A omega cos of omega t minus kx. A omega cos of omega t minus kx. What is this? Formula for velocity of oscillation of a particle taking part in the propagation of progressive harmonic transverse wave, which is at distance x at the end of t time. Correct? At distance x from the source of wave at the end of t time. Got it? Come on, Vp equals to a omega cos of omega t minus kx. Please remember this formula. We will utilize it in today's one of the numericals. Okay? Read down statement of first example in the illustrations. Read it? Come on. Frequency of wave they have given 96.7 megahertz. 1 mega means 10 raised to 6. Mega or million means 10 raised to 6. Megahertz is not the SI unit of frequency. SI unit of frequency is hertz. You must convert it into hertz. Come on, megahertz to hertz, just multiply by 10 raised to 6. And now V equals to F lambda. So lambda will be V upon F. Lambda equals to V upon F. What about velocity? They are talking about radio waves. Radio waves are nothing but electromagnetic waves which travel in air or vacuum with the same speed as velocity of light in vacuum, which you know it is 3 into 10 raised to 8 meter per second. So this velocity right now it is 3 into 10 raised to 8 meter per second, and then this frequency you must write in hertz. It is 96.7 into 10 raised to 6. Simplify, answer is 3.102 that many meter. What about wave vector? By formula k equals to 2 pi upon lambda. Pi value is 3.14. Lambda we have found out 3.102. Simplify. Answer is 2.024 and radian upon meter. See, what is wave vector? It is some sort of angle divided by distance. Unit of angle is radian. Unit of distance is meter. Correct? What about angular frequency? Omega equals to 2 pi f. Pi is 3.14. F is, come on, F is 96.7 into 10 raised to 6, and this multiplication comes out to be 6.07 into 10 raised to 8. Unit of angular frequency, you know, it is radian per second. Correct? Now kindly read the statement of sum number 2, illustration number 2. Read it? Look. Y equals to 0.5 into sine of x minus 60 into t, that means centimeter, is the given wave equation. As per the given format, you should write the standard format this way. Y equals to a sine kx minus omega t. Okay? coefficient of x is k, and here coefficient of x is 1, coefficient of t is omega, coefficient of t is 60. Okay. Now tell me, if they are writing omega t minus kx, then here also we should write omega t minus kx. Here if they write cos, we should write cos. Here if they are writing sin, we should write sin. Here they are writing kx minus omega t, then we should write kx minus omega t. So as per the format of given equation, we should set the standard format. Fine. Now compare. When you compare, this amplitude will become on 0.5 centimeter. So A is how much? 0.5 centimeter. Correct? Coefficient of x is k. Coefficient of x is 1. So k equals to 1. K equals to 1. But mind well, unit of k, don't write in hurry radian upon meter, because right now this y value is in centimeter. So you must write radian upon centimeter. What about k formula? You know it is 2 pi upon lambda. Then what is lambda? It is 2 pi upon k. Pi value is 3.14. What about k? K value is right now 1. K value is 1. 2 into 3.14, answer is 6.28. But because we are using here CGS unit, unit of lambda should be centimeter. What about omega? Come on, coefficient of t is omega, coefficient of t is 60, omega equals to 60 radian per second. Omega equals to 60 radian per second. What about omega formula? It is 2 pi f. Then what is f? It is omega upon 2 pi. Omega upon 2 pi. Omega is 60, 2 pi radian as it is. Instead of pi, I am putting 3.14. Simplify. Answer is 9.55 hertz. Unit of frequency is hertz. Symbol is capital S, small z. Leave proper gap. Write the symbol properly and don't put any full stop. What about periodic time? It is 1 upon frequency. Come on, reciprocal of frequency is called periodic time. 1 upon f value is 9.55. This answer is 0.105 that many second. Again, leave proper gap, write small s, don't put any full stop. And what about wave velocity? Wave velocity formula, look here. V equals to f lambda also you may use, no problem. You may use this omega upon k also. V equals to omega upon k. Come on, omega is 60 and k is 1. So omega is 60, k is 1, 60 upon 1, that is 60. And because you are using CGS units, CGS unit of velocity is centimeter per second. Centimeter per second. Got it? Come on, my dears. Now read this statement for illustration number 3. Have you read it? Look. V equals to f lambda. Anna? What is lambda then? It is V upon f. Velocity of wave is given to you in the statement 340 meter per second. Frequency is given to you in hertz only. It is 250 hertz. This upon this answer is 1.36 that many meter. It is wavelength. Okay. Now tell me, V is also lambda upon capital T. Don't you know? To travel distance equal to wavelength, any wave would take time equal to periodic time. And distance travel along the directional propagation of wave per unit time, it is called wave velocity. Fine. Come on. V is also, you can write x upon t, where x is the distance travel along the directional propagation of wave and t is the corresponding time. Distance travel along the directional propagation of wave in unit time is called wave velocity. Now this lambda upon capital T I have kept as it is. X also as it is. This time is given to you equal to time taken to complete 50 oscillations. What is the time taken to complete one oscillation? It is capital T. So for such 50 oscillations, total time taken would be 50 into capital T. So this small t is 50 into capital T. Correct? Come on, t and t will get cancelled. So x will be 50 into lambda. 50 into lambda. 50 as it is. Lambda we have found out 1.36. Correct? This into this answer is 68 meter. Okay. So at the end of 50 oscillations, the distance travelled by given wave must be 68 meter. Correct. Now read this statement of number 4. Read it? Fine. Here we have some tower of height which is given to 100 meter, and here we have some water pond, okay, some lake is there suppose. Then we just drop one stone, say at time t equal to 0 from the top of the tower, and what is the time taken by the stone to fall through this much distance? Come on, when this stone touches this water surface, suppose time is t. So in short, time taken by this stone to fall down by distance h, it is t minus 0, that is t time. Let us first of all find out that time. D equals to V0t plus 1 by 2 at square, second equation of linear motion with constant linear acceleration. Remember that? Fine. This distance traveled vertically downwards is equal to height of the tower, let it be h. For a freely falling body, initial velocity is 0, so this part is 0. 1 by 2 as it is. Acceleration for a freely falling body is gravitational acceleration shown by symbol small g into t square. Now tell me, h height is given to you right now 100 meter, 1 by 2 as it is, g value 9.8 meter per second square into t square. Find out t from here, you will get 4.52 that many second. But wait, at the end of this much time, this stone falls on the water surface. But when it falls on the water surface, the moment it touches the water surface, because of its impact, some sound is produced. And that sound is now reaching, that sound wave is now reaching to this person who is just dropping this stone. Okay. So now that sound wave generated from here has to travel this much distance equal to h. If velocity of sound wave is v, distance travel is h, and corresponding time taken is suppose t dash, then find out t dash. T dash will be h upon v. T dash equals to h upon v. Distance traveled by sound wave from here to here, it is h, which is 100 meter height of the tower. And what about v? V is the velocity of sound wave. They have given in the statement 340 meter per second. This upon this answer is 0.29 second. Wait, what is the time taken by the stone to fall from here to here? That time is 4.52 second. After 4.52 seconds, sound is produced here, and that sound wave takes additional 0.29 second to go from here to here, correct? So what is the total time at the end of which the person who is dropping the stone will hear that sound? That total time is t plus t dash, t plus t dash, t plus t dash. What is t? 4.52. What is t dash? 0.29. Make their addition, answer is 4.81 second. Okay. Leave proper gap, write small s, don't put any full stop. Okay. Kindly read the statement of number 5. Have you read it? Look, they have given one wave equation which is y equals to 5 sin 30 pi into bracket t minus x upon 240 that many meter. T is in second and x and y they are in meter. Fine. First of all, take this 30 pi inside. Actually, one must not write this way because sin 30 pi is 0. Sin 30 pi is 0. You cannot write this way. Okay. You must put curly bracket here. Please. Take this 30 pi inside, then 5 into sin as it is, and 30 pi when you take inside, 30 pi t minus 38 is 240, so it is now minus pi by 8 into x, minus pi by 8 into x, that many meter. And now this equation you can compare with the standard format. What is it? Y equals to a sin omega t minus kx. Y equals to a sin omega t minus kx. Fine. Now just compare. When you compare, you will get amplitude how much? 5 meter. Omega, angular frequency, 30 pi radian per second. K, wave vector of the wave, pi by 8 radian upon meter. Wait. Now, when you take time t equal to 0, that is beginning moment, when you are talking about the particle which is located at the source of wave, just very first particle at the origin, then you can put x equal to 0, just put both the values here, come on, x is 0, t is 0, x is considered to be 0, t is considered to be 0, then this part will be 0, sine of 0 will be 0, 0 into 5 will be 0, so y equals to 0. So the particle at the origin at time t equal to 0 is at equilibrium position, fine. Now you are talking about particle at the origin of production of wave, then you can put x equal to 0. Come on, when you place x equal to 0, this part will be 0. So left is y equals to 5 sine 30 pi t, y equals to 5 sine 30 pi t, correct? So we are talking about that particle which is located at the position of source of wave, fine. And now as this time is, suppose time you are taking first of all 0, put t equal to 0, this part will be 0, correct? But then when the time will increase from 0 onwards, first of all this angle will enter in first quadrant. When t will start increasing from 0 onwards, first of all this angle will enter in the first quadrant. And you know, in the first quadrant sine function is positive, positive into positive is positive, so y value will be positive. So I mean to say value of y will first increase along positive direction, that is vertically upwards. So you will get crest, you will get crest. So at the position of source of wave, first of all you will have the crest which is getting produced, correct? Fine. So our answer is crest is getting produced first, fine. Then after they have asked displacement of a particle which is at distance 480 meter from the source of wave at the end of 2 seconds. Let us find out displacement now. Use this equation of displacement, y equals to 5 sine 30 pi t minus pi by 8 into x. Put up the values. Time t is given to 2 seconds and this distance is given to 480 meters. Simplify now. 30 pi into 2, that is 60 pi. 8 6 is 480, 60 into pi I have written here. 60 pi minus 60 pi, that is 0. Sine 0 0, 0 into this will be 0. So y equals to 0. Okay, come on. They also asked the velocity of oscillation of the same particle. Just now we had obtained the formula for velocity of oscillation of particle during the propagation of harmonic wave. What was that formula? Vp equals to a omega cos of omega t minus kx. Remembered? Vp equals to a omega cos of omega t minus kx. Put up all the values. A is how much? A is come on 5 meter. A is 5 meter. Omega is come on 30 pi radian per second. Cos as is omega is 30 pi radian per second. Time is given to 2 seconds. K value, come on compare. K is come on pi by 8 radian per meter. X distance is given to in the statement 480 meter. Simplify now. 35 is 150 into pi. Cos as it is 13 into 2, that is 60 pi minus 480 upon 8 will give you 60 into pi. 60 pi minus 60 pi, that is 0, cos 0 is 1. Pi value is 3.14. If you multiply, answer is 471. SI unit of velocity is meter per second, correct? Mind well, this is not velocity of wave, this is velocity of oscillation of particle, fine. And at last they have asked about the slope of wave pattern, During the propagation of harmonic wave, the pattern developed along the direction of propagation of wave is found to be like this as per sine curve, Now when you are plotting this sine curve, actually it gives you at a given moment, it gives you graph of y versus x. At a given moment, when you take the photograph of the whole pattern, you will get in the photograph curve like this, which gives you graph of y versus x. X means distance of a given particle from the source of wave, y is its corresponding displacement at a given instant of time. And now, slope of a curve means slope of a tangent. Slope of a curve means slope of a tangent. And because you have graph of y versus x, what should be slope? Slope should be y, dy upon dx. For a graph of y versus x, what is the slope? Dy by dx. So now it is d by dx of y. D by dx of y. According to wave equation, what is y value? Y equals to a sine omega t minus kx. Expression of y is a sine omega t minus kx. Y equals to a sine omega t minus kx. Correct? This a is constant, can be taken out. Derivative of sine is cos. Correct? Now go inside. Come on. When you are talking about different particles, that time you should consider the given moment of time. So when x is being changed, this t should be taken as constant. Because omega is constant and t is constant, this part is constant. Derivative of a constant part is 0. Minus k as it is. Come on, d by dx of x, it is 1. D by dx of x is 1. Correct? When you take here derivative with respect to time, suppose, then treat x as constant. When you take derivative with respect to x, then treat this t as constant. Okay? Now this is minus a k cos of omega t minus kx minus, what is a? A is, come on, 5 meter. A is 5 meter. K is how much? Pi by 8 radian per meter. Cos omega is 30 pi radian per second. Omega is 30 pi radian per second. Given time is 2 seconds. K is pi by 8 radian upon meter. What about x? Come on, distance of a given particle from the source of wave, it is 480 meter. Simplify now. 32 is 60 into pi. 480 upon 8, that is 60 into pi. 60 pi minus 65 is 0. Come on, cos of 0 is 1. 1 into this part will be same only. Minus 5 pi by 8. Minus 5 pi by 8. Okay? No unit because you are finding dy by dx. So distance upon distance will have no unit. Correct? And what does this negative sign indicate? The slope of a tangent is this much, which is negative, meaning thereby the tangent must be like this. And the tangent indicates that as x increases, value of y decreases. Correct? As x increases, value of y is decreasing. That's why slope is coming out to be negative. Okay? Fine. What about wave velocity formula? V equals to omega upon k. V equals to omega upon k. What is omega right now? 30 pi radian per second. K is pi by 8 radian upon meter. Omega is 30 pi radian per second. K is common pi by 8 radian upon meter. Pi will cancel. Denominator will become numerator. 38 are 240. SI unit of velocity is meter per second. This is wave velocity, and if phase speed is asked, phase speed, then also it will be the same only, because recently we have proved that whatever is the wave velocity, same is the phase speed. Okay.